Welcome back to another video on congruence, just those basic ideas of congruence. So we've been going through the first few pages of the packet. If you don't have the packet, you can still develop an understanding of congruence. And today we're going to focus on determining if more figures are congruent. In this case, we've got three different figures here in example number 3. Which two of them are congruent? Well, we can easily see which ones are not congruent by finding one length that actually doesn't match. We don't need to look at the whole figure, we just need to look at one length. And an easy way to do that is to just take a quick look at this. This increases by 4. So the length of this line segment is going to be 4 on our grid. But if we look at the other figures, there's no length of 4. This one does go up 4, but it also goes over 1. So if I use the Pythagorean theorem, this one is actually going to be the square root of 17, which is a tiny bit bigger than 4. If it was 4, it would be the square root of 16 for that. And I was able to get that by doing 4 squared plus 1 squared is 17 squared, or 17, and then we take the square root of that. So this length does not match that. So these cannot be congruent, even if the rest of it is. If we do the same thing over here, this is a 4 and a 1, definitely not congruent with this 4. So an easy way to determine if you have things on a grid, if certain lengths are congruent or not, is just take a quick look at those lengths and see if they produce the same slope triangles or similar slope triangles. All right, so we know that EFG doesn't have a pair, so the two congruent triangles have to be these two. Now, since we're looking at determining if they're congruent or showing if they're congruent, the next thing we're going to do is actually go through the process to show that these two are congruent. And there is a pretty simple 3-step process to do. Okay, so we're going to talk about that as soon as my text box can come up. There we go. All right. If I want to show that two figures are congruent, I'm going to do this 3-step process that makes it pretty easy to judge congruence. All right, I'm going to make this a little smaller. So step one is pretty simple. We're first going to translate. So 1 point, and I'm going to put at least 1 point, matches. We'll talk about what that means in just a second. Step 2, after we translate, we're going to rotate. So at least one side matches. Okay, and then finally, we're going to reflect. So all sides match. Okay. This is going to be our process to determine if two things are congruent. Now, one of the beauties of using these 3 steps is it works with a grid, without a grid, it works anywhere we've got it. And we're going to see how that works in just a second. But before we do, I want to make sure we understand one thing. We can skip steps. Okay? You can skip steps if you translate, rotate, and reflect. Maybe you don't need to rotate. Maybe you don't need to reflect. We can skip some steps here. All right, let's go ahead and see how they're congruent. If I take a look at my figure ABC, I know that it's going to match JKL. So I kind of want to pick a side that or a point on each figure that I think I know matches. An easy way to do that is to look at the corresponding lengths. So if I look at C to B, it goes over 3 and down 1. So I need one that either goes down 3 over 1 or over 3 and down 1. And the only one that does that is L to K. So either C is L or C is K. Just looking at the two figures, C and L are going to be the same. So I'm going to translate this figure so that C lands on L. Okay, now this works. I could describe it as going over 2 and down 3, but this works whether I'm describing it like that or not. C landing on L. All right. Now, after I translate, Remember, my step 2 is to rotate, so one side matches. Now, the rotation, I'm going to use my center at that same point in our figure. So the rotation is going to be at point L, because I don't want to move C and L. C needs to stay where L is, so I'm going to rotate it around there. All right, now, as I rotate it, I can rotate it in 2 different directions. I can rotate it this way, so that lands. And I said 2 different directions, but really what I meant is I can rotate it 2 different lengths in each direction. I can rotate it there, so that side matches, or I can rotate it here, so this side matches. Okay? Or I can just go back. I can also rotate clockwise and do the same thing. So if I rotate clockwise, this side's got to match. And then I can go over here, this side's got to match. Regardless as to which one I do, I want to get those sides to match. There we go. So my second transformation is going to be a rotation. I'm going to rotate around L so that one side matches. And an easy way to describe this is just to think about what point met. So this is my long side here. So see my long side, that's A. A rotated and landed on J. So I'm going to say rotate around L so that A lands on J. If I were to go the other way and get it up there, then I would want my B to land on K. All right, so B would land on K if I rotated it further, if I rotated the other way. All right, so here's my rotation. After I do a rotation, I'm going to do a reflection, so all sides match. In this case, we needed to do all 3 of them, and my reflection is pretty simple. I can reflect across this line, LJ, and that point will just go right over there. So I'm going to say reflect across line LJ. And whenever I translate, I rotate and reflect, my figure will land perfectly on top of the other. Now I still want to list an input and an output, so I'm going to put an input A, B, C, and then that's going to produce J, K, L. This order matters. If you take a look, I put A and J in the same spot because A and J are the same coordinate in their respective triangles, or the same point in their respective triangles, same vertex. B and K are also the same vertex, and C and L are that same vertex as well. This order does matter. We're going to focus on that a lot in this chapter. The next thing to note is that this isn't an answer to a question. Are the triangles congruent? This is the reason for our answers. We know the triangles are congruent because of these transformations. Okay? The translation, the rotation, and the reflection. We know the triangles are congruent because of that, so this is really our reason. Because we have a reason, we also need our statement, and our statement is just that the triangles are congruent. So I'd write it like this: triangle ABC is congruent to triangle JKL. Okay, those 2 triangles are congruent. And so this is our actual statement. As we've been going through, one of the big things we focused on is statements and reasons. And so we want to make sure we understand which one's our statement and which one's our reason. All right. Go on to the next problem and see if you can tell which 2 are congruent. And if they are, try and come up with the transformations to do them and then write that final statement. If you can't find them, find out the transformations that'll work, or they don't look congruent to you, then try the other one. Okay? Both of the questions kind of go like that. Are A, B, C, D, E, and J, K, L, M, N congruent? Pause real quick before I give you the answer and before I go through it with you. All right. So hopefully you paused the video and you were able to take a look at this. Now, I want to know if JKLMN and ABCDE are congruent. Now, in order to determine if they're congruent, I just want to look for sides that may not match up. And I can see a simple side that doesn't look like it matches up. If I look at ED, that goes up 1 and over 2. If I were to use the Pythagorean theorem on this 2 by 1 triangle, that would be 4 plus 1, which is the square root of 5. I would have a length that's the square root of 5. Now, if I look at its equivalent side, that should be j to n. That goes 2 and 2. 2 squared is 4, plus 2 squared is 4. This is actually going to be the square root of 8. So, are these congruent? No, because they don't have the same slope triangle. That allows us to say that they're congruent. These slope triangles are slightly different. So we can say that ABCD is not congruent to JKLMN. And I'm going to write it out this way. ABCDE is not congruent to JKLMN. Okay? Those are not congruent, and to show that they're not congruent, I put a cross through my congruent. Now, this is my statement. So what's my reason? Well, my reason is I found out that JN is not equal to ED. So I'm going to say because JN is not equal to ED. And that line segment should be equal for it to work. To say that it's not equal, I'm going to put a cross through the equals. All right, what about ABCD and VWXYZ? Let's see. I used ED before. That's a 2 and 1, 2 and 1. So those lengths are the same. What about this one? This goes over 3 and up 2, 2 over 3. So that one works. 4 and 1, 4 and 1. That goes over 3, that goes over 3, and 3 and 1, 3 and 1. So this is congruent. All right. So since I wanted them to be congruent, I was able to see that these definitely have all the same lengths, but what transformations will work? Well, let's start off by drawing the pentagon for ABCDE. There we go. Okay, and I'm going to move that around. Now, I want to move it and translate so that at least 1 point matches. Luckily, in this case, I've got 1 point that matches pretty easily. If I look over here and I look at B, I can move it directly to W and they'll match perfectly. So I'm going to first translate so B lands on W. Translate so B lands on W. All right, next, I could rotate, or I could try to rotate, but the whole point of a rotation is that so at least one side matches. Well, take a look. I already have one side matching. BC, which was here, is now here at WX. So I already have one side that matches. So I don't need to do my rotation. I can skip it and go directly to the reflection. Now, if I reflect, I want to flip it, but I don't want to reflect across an axis. I can reflect across this line. And so I'm going to reflect across WX. So I translate A, B, C, D, E, and then I reflect across WX, and it becomes V, oh, that's W, V, W, X, Y, Z. Okay, translate, then reflect, and I've got my new figure. Awesome job. Okay, but again, this is just a reason, so I'm going to write down my statement. So, A, B, C, D, E is congruent to V, W, X, Y, Z. So they're congruent. Awesome. All right, we just got a little bit more to go through. And for this, you're going to go through a lot of it yourself. Take a look at each of these figures. You've got 3 here, and then on the next page, you've got 2 more. Are these figures congruent? Okay, so you want to get your statement together. These 2 puzzle pieces, they're definitely congruent. Okay, now, how do I know that they're congruent? Well, you don't need to give out many details, but try and give out the one. In this case, it's a reflection. Okay, they're congruent because it's a reflection. Now, it's also a good idea to draw the line of reflection. There you go. If I reflect right across that line, I know that they're congruent. Take a look at B here. Are those congruent? Take a look at C. Are those congruent? Now, with C, you're going to have to come up with 2 transformations to show that they're congruent. What about A here? Are these congruent? You could do 1 transformation or 2, depending on what you're thinking. For B here, are these congruent? Hopefully your answer is no. All right, and we've got one last thing for you to do. Take a look at a real-world kind of situation. Now, if you like working with wood like I do, then a transformation like this is something you may want to do in order to get a good wooden joint. Now, take a look at A and B. How would you transform A to get it to land on B? Pretty simple thing to do, so I want you to write down your details here. Write down the transformation. What composition would take A to B? Now, it could just be 1 transformation, could be more than 1. All right, and what composition would take A to C? Notice how they both have that same kind of curve, but they're in different locations. So what kind of transformations would take A to C? Pause the video, and I'll give you those answers real quick in just a sec. All right, to go from A to B here, we would just translate. So we're going to translate A, and we're going to produce B. Now, as for how far down we need to go from A to B, I'm not sure. We're not going to write down a specific detail, but we want to make sure we understand to translate A to get B. We can add down here just as a nice descriptor. To make A to B, we're going to translate down. For A to C, we've got a few things we need to do. Well, C's a little further down than A, so we're probably going to have to translate down, but it's also facing the opposite way. So would a reflection work? Well, if I reflected A, it would look like this. Okay, I'm going to try and do this pretty well, but I don't know how well I'm going to do. It's going to go like that. It won't be the same as C. I would need to do 2 reflections, or just shift it down and then do a rotation to get it like C. So that's what I'm going to write down. I'm going to say, take A, and I'm going to translate it down. After I translate, then I'm going to rotate A, or then we'll rotate so that A lands on C, and it looks like it's going to be about 180 degrees. I can tell that because this side ends up on this side. All right, and if I do that, that produces C. Don't forget to practice including your inputs and outputs here. It's a good skill to learn. All right, and with the next time, we're going to get to not lesson 4.2. We're actually going to skip that for now and come back to it in just a little bit. But we're going to go on to lesson 4.3. Hope you guys learned a lot, and have a good day.